Hey everyone, my name is Venkatesh. I'll be hosting the session on behalf of Skilling. For those of you engaging with Skilling for the first time, we are an engineering upskilling platform with a focus on emerging technologies. This webinar is brought to you by our enterprise business, which focuses on employee training and upskilling across various industries, including automotive, consumer electronics, ITES, etc. Today's webinar is on mechatronics and embedded systems for future vehicles. Some pointers during the webinar. I request everybody to post your questions on the chat window. Mr. Ravindra will take it up during the end of the session. We will share a feedback form towards the end of the session. Please spare a minute to fill it up. We'll not be able to share the deck. However, we will be able to share the recording of the session if you request the same in the feedback form. Moving on to today's instructor, Mr. Ravindra. A brief introduction about him. Mr. Ravindra Nelikunja is a automotive embedded systems expert with over 30 years of industry experience. A former VP R&D at Bajaj Auto Limited, he has been a key leader in the automotive and electric mobility space, specializing in E&E architecture design, software-defined vehicles, connected and autonomous technologies, and cost-efficient innovative design concepts. He has led large R&D teams, guided NPDS initiatives, and contributed to strategic sourcing, localization, regulations, and design due diligence. We are excited to host and hear from you, Mr. Ravindra. Over to you.
Thank you, Venkateshwaran, for the introduction. And good afternoon and welcome all the participants for this webinar on mechatronics and embedded system for future vehicles. Am I clearly audible?
Yes, Mr. Ravindra.
Okay, thank you. So broadly, the agenda for today would be like first we would have the introduction, industry shift from ICE to EV SDV. Broadly, I'll be covering it in around 15 minutes time. Then we'll have automotive electronics and embedded systems, which I would cover in 20 minutes. Also, then we would have vehicle networking and communication. Broadly, I would be spending around 20 minutes on these topics, followed by integration and testing, around 15 minutes. And finally, we would have a wrap up and question answer session of around 5 minutes. So in the introduction, we will deep dive on the industry megatrends, regulatory push, how engineering focus is shifting from mechanical to electronics, and we would touch base on a case study of how Exide is transitioning from lead acid to a lithium-ion battery supplier. In the automotive electronics and embedded systems, we will deep dive on role and growth of ECUs, sensors and actuators, embedded controllers and software, integration of electronics with mechanical systems, and have a case study of Bosch scalable ECU platform. Coming to the vehicle networking and communication, very important topic. We will touch base on why in-vehicle networking is needed. What are the different protocols overview of CAN, LIN, FlexRay, and Ethernet? Cybersecurity challenges in connected vehicles, and a case study of Motherson Ethernet integration. The last topic would be on integration and testing, where we will be covering the wiring harness basics, harness the nervous system of the car. Then we will touch base on testing and validation basics. We would also cover functional safety ISO 26262 considerations and a case study on ultra wiring harness design and Bosch best practices in validation. And finally, the wrap up and summary session and question answer, where mainly the focus for future automotive would be lying in EV, ADAS, SDV, and connected vehicles. and especially for mechanical engineers, the areas to focus would be on basic electronics, communication protocols, testing methodologies, and model-based development. So let's look at what are the automotive industry megatrends. Broadly, there are four which are driving the shift of automotive industry from predominantly a ICE-driven development to more of a EV software-defined vehicle uh, areas. So first is the electrification. In terms of the penetration, we are already seeing very good penetration, especially, for example, in the two-wheeler space, three-wheeler EVs, both passenger and cargo, and also in the commercial vehicle space. Uh, Also in the passenger vehicle, more than 5% penetration is already achieved and has got good tailwinds to achieve more electrification. But predominantly, it's more of a urban city phenomena. But going forward with the charging infrastructure and other range-related anxieties and acquisition cost being addressed, the penetration of EV is going to further increase. Next parameter, which is making the automotive industry shift to EV SDV, is the connectivity. Previously, in the ICE world, the vehicles were standalone and mostly used for only for commuting purpose. But today's vehicle are more smart and they are connected to the external world, and basically they are now called as software on the wheels, and which is all enabled through the connectivity feature and of course the infrastructure enabler like 5G network and all other technologies. And the third driver for rapid gain in software-defined vehicles and shift from ICE is the autonomous driving vehicles, and especially in which the regulatory push for ADAS level 1 and 2, which is making a shift to the EV HDV space. And the last key driver is the digitalization, where more and more software and data integration is happening, and technology enablers like artificial intelligence, machine learning, and model-based systems are being deployed in a large extent compared to the previous standalone ICE development. So in terms of megatrend in automotive industry, the basic key driver has been the CASE acronym, basically connected, autonomous, shared, and electric. So electrification is shifting the propulsion system from predominantly gasoline to EVs, hybrid, and hydrogen. Connectivity is transforming the vehicles into computers on wheel, especially enables data-driven services and revolutionary over-the-air updates and cloud integration. Autonomous vehicles again has a lot of advancement in advanced and self-driving technologies. In the Indian context, it is still in nascent stage, but in advanced countries, full-fledged autonomous vehicles are also gaining a lot of traction. But at least in the Indian context, the level 1 and level 2 are being implemented mainly from regulatory point of view. And the digitalization, mainly the software-defined vehicles, artificial intelligence, and data-driven ecosystems. So, as I earlier mentioned, the industry megatrend has been to encompass a software-defined vehicle. So let's look at what are the key features of a software-defined vehicle. So in terms of concept, the vehicle features are controlled and updated via software, unlike in the ICE where it's predominantly more mechanical nature, or it would be like a fixed architecture where any change means it's you need to start from scratch the development. And also, like the software-defined vehicles have a very innovative feature like update over the air. So, in terms of the feature, in terms of the firmware, or in terms of the diagnostics, a lot of things can be done remotely with this over-the-air update. And because of all this, the software-defined vehicles behaves like a smartphone on the wheels. If you look at what are the key enablers driving the software-defined vehicles, principally they are the centralized E architectures, which has the zonal controllers and very high performance central computers, high-speed networking backbone, primarily driven by Ethernet, which can handle large data flow, and connectivity to the cloud through which a lot of services with the external world can be exchanged and shared. And also the feature of AutoSOAR adaptive dynamic helps in collaborative development with the different vendors and the OEM. So in terms of the benefits, this software-defined vehicles help in rapid innovation and update, reduces the hardware complexity, unlike in the past where ICE were more like a black box ECUs. The ECUs used in EV, the hardware is pretty much standard, but what adds more value and complexity into the system is the software, which is embedded software, which sits on, and the control algorithms which resides on the embedded system. Because of this, all these things, the software-defined vehicles have more flexible development life cycle, has more usability in terms of the platform, can personalize the customer experience to large extent, and enhance the vehicle longevity. Another important thing what I want to highlight here for a EV or for a software-defined vehicle with respect to a ICE vehicle is as far as the OEM and the ecosystem is concerned. In case of a software-defined vehicle or EV, the transaction with the customer is lifelong throughout the life cycle of the vehicle, because the features can be updated. Any bugs can be corrected because of the word Arab features, and a lot of predictive and maintenance and diagnostic features can be are incorporated in this new generation vehicles, which were not possible in the past with standalone ICE vehicles, where suppose there were some innovative features which are come into the market, then the only choice left to the customer was he need to upgrade his vehicle. Whereas today, I mean, the features can be upgraded on an old vehicle which a customer has bought. So that's the revolutionary change, which is this software-defined vehicles, electric vehicles are bringing into the horizon. And of course, there are challenges like, for example, software complexity is increased. The domain knowledge required is very much talent scarcity is there. In terms, since now these vehicles are communicating with the external world, cyber security threats are there, and validation and homologation are much more complex and requires very stringent testing. Now let's just look at what are the main key differences between an ICE vehicle and EV or a software-defined vehicle. So the left predominantly captures what's the key attribute for an ICE vehicle. Mainly, it's engineered for a specific powertrain and any change, and it is primarily driven by a mechanical control system. So any change requires a totally new development grounds up, unless of course the changes are minimal and manageable in the same platform. In terms of vehicle architecture, they are more distributed ECUs, where each ECU controls a specific function. And I mean, in terms of the deployment of electronic and software, electronics, of course, is deployed, but they are more dedicated in function. But in terms of software, it's mostly a application specific deployment. So there is limited software role for, and all changes happen are manually updated. So in terms of connectivity, the connectivity is mostly restricted to infotainment. And in terms of engineering skill set required for the development, mostly it's a more of a platform driven where a dedicated architecture and all the sizing of the components are done, which is more mechanical driven. And in terms of accommodating any changes based on the real dynamic driven world, it's very tedious and difficult and very time consuming. Unlike all these things, when you come to the electric vehicle or software defined vehicles, so the entire key functions are controlled, updated, and optimized by software of the vehicle. The architecture which is conceived for a software driven vehicles are agnostic to any specific power function. So it could work well for either electric vehicle, hydrogen, or any specific chemistries. So it's agnostic to any specific powertrain. So it's more of a functional domain where so all the functionalities are controlled through the software like electric drive control, autonomous driving, cockpit infotainment, and part of that. In terms of connectivity and cyber security, it's highly connected, highly regulated, and in terms of cyber security, it is highly focused in terms of the security and all the encryptions are in place since it's constantly interacting with the external world. And the important thing, as I mentioned earlier, is the software defined vehicles in terms of the value proposition and engagement of the OEM and the customer. It is a lifelong from the purchase of the vehicle by the customer till its end of life. The OEM and the customers are constantly engaged, both in enriching their customers' user experience and also in terms of generating revenue through the data-driven revenue streams. Now, let's also look what is pushing the vehicle architecture from ICE to EV. So mainly in terms of the regulatory push, they are the emissions, the vehicle safety, and the cyber security. In a regulatory push, mainly in the emission norms in India, tightening of standards of BS6 phase 2 is happening. Euro 7 in European Union is happening. So effectively what this means is in terms of carbon monoxide, nitrogen and other things. Sorry. In terms of meeting the emission, it's getting stringent and stringent. And also there are carbon credits which people can carry if they have an EV in their portfolio. So that's what most of the OEMs are leveraging to mitigate some of the areas where it's very difficult to meet the emission norms. So zero emission targets, accelerating EV adoption and carbon neutrality in the next 2 decades. Again, with acquisition cost coming down and the ecosystem developing, there is going to be a lot of impetus in this area. And the life cycle approach where well-to-wheel emission and battery recycling compliance, this also is going to enable the shift. In terms of the vehicle safety regulation, mainly the mandatory ADAS level 0, level 1, crash norms and Bharat NCAP ratings pedestrian protection and active safety technologies, incorporating sensors, cameras, and automatic emergency braking, and deployment of the functional safety ISO 26262 compliance for software and electronics, which is being implemented in very sophisticated way in the Europe, in the advanced markets abroad, but slowly in India also, because most of the things are safety critical. ISO functional safety is becoming mandatory for many of the subsystems. In terms of cybersecurity and data protection, as I mentioned, like the over-the-air software updates and interaction of the vehicle with the external world. So cybersecurity is becoming critical, and in terms of external threats is increasing. So in terms of the protections and the encryptions and the safety, there's a lot of work happening for data protection and privacy. India is also aligning with AIS standards, their AIS standards with the global norms. That means it's going to be more competitive and aligning with the global best practices. So the key focus in case of cybersecurity and data protection would be having more secure over-the-air updates, encryption, real-time threat monitoring. So now let's look at how engineering focus is shifting from predominantly a mechanical to an electronic driven development. So if what you see on the left side is more a mechanical driven approach, predominantly in the 80s and 90s, that's how it was. Like the powertrain primarily was driven by more of mechanical parts, where any changes you need to change the specification of the gears and the solenoid valves, actuators. But today, most of these functions can be controlled using the sensors, actuators, ECU, and the wiring. So in the mechanical era, mostly the focus was on engines, transmissions, gears, and the fuel systems. So it was very, inflexible and very rigid. I mean, any change required, you need to do a lot of redevelopment from scratch. So to that extent, in terms of development time, continuity, reusability, it was not that flexible. But and also it was dominated by mechanical design and manufacturing expertise. So in terms of many times the design would specify something, but suppose let's say the manufacturing drawing would not adhere to that in terms of tolerance or the material or in terms of the heat treatment, other things, then the end result would be in terms of functionality, there would be unintended functionality and eventually leading to loss of function and a loss of durability. Also, in terms of innovation, it would be an incremental innovation in efficiency and durability. Now, when you compare with the mechanical era, in the electronic era, mostly the focus is on electronic control units, the sensors, softwares, and wiring architecture. So mainly, it's like plug and play, nothing specific. All are being configured based on the application specific. But we need to keep in mind, I mean, when the application is being defined, the electrical system architecture has to be defined and robust to cater to the future. Only then the scalability and plug and play would work. So all this is possible mainly because in the shift in the technology and availability of very high power computing semiconductors with lot of memory and at a affordable rate. So I mean, you can take a corollary. I mean, in the 80s and 90s, a desktop which used to be very huge and with limited computing would cost a fortune. But today, a laptop would has lot of enormous multitasking computing power at a reasonable price. The same corollary is for vehicle, where the electronics has evolved over a time, and that has given the flexibility for going for software-defined vehicles, which has much more flexibility in terms of architecture and the roadmap for product development. So growth in embedded systems, software integration, and data management, and innovation is primarily driven by connectivity, automation, and electrification. So in short, the automobile is transforming from a mechanical machine to a software-driven electronic systems on the wheels. So let's just take a case study of how the ecosystem, especially the vendors, are evolving based on how the industry is moving from a predominantly ICE world to more EV-driven world. So the case in point is Exide. Predominantly, they're a well-known name in the industry for supplying lead-acid batteries. So those were primarily used for low voltage application in the ICE space. But when they sense that the world is moving to electric vehicles, deploying high voltage batteries and battery being the key energy source for driving the vehicle. So as part of the business de-risking, they also have entered into they shifted their strategic focus and transition towards developing advanced lithium-ion battery technology to align with EV and energy storage market trends. So they're coming up with a green park facility at Bengaluru for a 12 gigawatt cell, predominantly LFP, as part of the phase PLI scheme. And primarily, the application of these batteries would be in the two-wheeler and three-wheeler EVs, the e-buses, and the energy storage system. So principally, Exide has part of their de-risking has entered into the high growth EV system while maintaining its established lead in the lead-acid business. And technology-wise, they're localizing to reduce the import dependence and strengthening sustainability and innovation position to meet the future needs. So next topic is the automotive electronics and embedded systems. So basically, the role and growth of ECUs has been the one which has triggered phenomenal impetus to the automotive embedded system. So historically, if we see in the 80s and 90s, a passenger vehicle, high-end passenger vehicle used to have maximum 10 to 20 ECUs. Today, a medium to high-end can easily have more than 100 to 150 electronic control units, and its numbers are growing based on the features and the sophistication of the vehicle control. So, in terms of the functionality of the ECU, so basically you can compare it to the central nervous system of the modern vehicles. Primarily, it controls, manages, and optimizes the vehicle functions through precision electronic control, enables performance, efficiency, comfort, and safety, and seamlessly integrates the hardware, software, and communication network. So, from a customer point of view, it enriches the user experiences, handling all the complexities in the background. So in terms of the growth trend, as I mentioned, from around 10 to 20 ECUs, it has grown to northwards of 100 ECUs in the modern vehicles. In terms of the architecture, predominantly from a distributed ECUs, each ECU controlling a function, it has now moved to more of a centralized zonal domain and zonal architectures. And today's ECUs are primarily defined so that software-defined vehicles driving integration and OTA updates are supported by these ECUs. So the key ECU domains are the powertrain ECUs, which primarily controls the engine, motor control, transmission, energy management. The body ECUs, lighting, HVAC, doors, seats, windows. In terms of the ADAS ECUs, primarily they are controlling data fusion, mainly the sensor, camera data, radar fusion, braking, and steering assist. In terms of infotainment and cockpit ECUs, it's the connectivity, navigation, voice, and HMI systems. And in terms of the BMS ECUs, it's the battery health, charging, thermal management, and safety. So one thing what I'd like to highlight here is earlier also in the ICE world, ECUs were there, but they were more catered to a particular function. For example, for a fuel injection system ECUs. So primarily that ECU cannot be used for a body control because the way the hardware and the software has been configured was for a dedicated function. So it was primarily configured for a typical function of fuel injection, and it was catered for low cost, high volume application. So any feature change required a total engineering change. Whereas the concept today is you have more general purpose ECU, but add more feature enrichment through the application software layer, which is all software driven. So that's the primary difference which is coming into the play. And of course, all that is enabled using the sensors and actuators and the engine control unit. So now let's look at what are the sensors and actuators on the vehicle. So this has got a very important role to play in the entire control algorithm and ensuring seamless user enrichment of the features. So, I mean, a sensor can be considered like a vehicle sensing organs. So it detects the physical parameters and provide data to ECUs for control and monitoring. So the typical sensors are used on the vehicle could be temperature sensors, mainly for engine, battery, cabin, and motor. Pressure sensors for fuel, oil, air, tire pressure, etc. The position sensors, basically the pedal, steering, throttle, gear position, etc. Ultrasonic sensors, mainly for the ADAS application for parking, obstacle detection, and lidar sensors again for ADAS application, autonomous applications for the 3D mapping for ADAS and autonomous driving. In terms of the actuators, it can be considered as the vehicle's response mechanisms. So here basically it converts ECU commands into physical actions. So in short, you can consider the sensors to be input to the ECU and the actuators to be the outputs which are controlled by the ECU. So, so the actuator converts ECU command into physical actions. So for example, the typical actuators on the vehicle are motors used for windows, window lift or seats and mirrors, relays used for switching high current circuits under ECU control, the valves which are used for regulating fuel, air, coolant, and hydraulic flow. Predominantly, again, in terms of actuators, the solenoids and valves are now being more replaced by electric motors, especially the BLDC motors, which are more energy efficient and can be controlled efficiently for using the PWM control for better energy efficiency. Sorry. So in short, the sensors feed the data, ECU processes it, and actuators execute it. In short, this is how the role of sensor, actuators, and ECU is on in the vehicle. And because of the control algorithms, a closed loop control ensures precision, safety, and efficiency of how this system works to get the intended functionality working properly. Next, let's look at what's the embedded controller, which is the vehicle's digital brain. So essentially, in terms of the components, it has a ECU where microcontroller is the main part. Then there are sensors and actuators, and the software resides in the microcontroller in the ECU. So in terms of functionality, the microcontroller controls specific vehicle domains like engine, brakes, BMS, etc. It integrates the central processing unit, memory, and input and output for real-time control. It also ensures reliability, low latency. Latency means response time, and meets all the safety standards like functional safety and other requirements. In terms of the software layers, we have the real-time operating system, which you can correlate to human heart, which regulates the heartbeat and pumping of the blood. Similar function the real-time operating system does in terms of multitasking, in terms of scheduling, and in terms of interrupt handling, so that in the background all these functions work seamlessly and ensure that deterministic performance for safety and reliability is achieved. Few of the examples of the real-time operating system deployed in the automotive world is OSAC, QNX, FreeRTOS, AutoSAR OS. Mind you, all these are mostly open source operating systems, unlike in the past where proprietary softwares were used and it was more like the ECUs and the software were black box. Today we are moving into a world where it's more collaborative driven development where all the open source and it's like people following AutoSAR and necessary standards ensure that seamless exchange of data and collaborative work happens. So in terms of AutoSAR, so basically, as I said, it's a standardized software architecture. What does it do? It enables software reusability and interoperability across ECUs and vendors. So, sorry. So this feature is extremely important in the today's collaborative world for seamless exchange of information and data. So the classic platform basically is used for real-time issues like the powertrain, chassis, fuel injection, ABS, and stuff of that sort. The adaptive platforms are used for high-performance issue applications like ADAS and infotainment, which are high-speed and critical, mission-critical functions. So in short, deploying the AutoSAR helps in supports in modularity, scalability, and safety compliances. So in short, the embedded controllers plus standardized software has helped in foundation for the modern software-defined vehicles. So a powerful embedded controller with a feature-rich software residing on it has enabled software-defined vehicles where all the vehicle control functions are controlled by the software. And in short, and overall, it is enriching the user experiences. And again, as I said, it's always, I mean, as some features get enhanced and suppose, let's say there are some known issues on the vehicle. So all those things are corrected real time on the vehicle without the customer suffering because of all this, I mean, facilities available in the embedded controller and the software enhancement. Now let's look at the integration of electronics with the mechanical system. So basically, in terms of integration, So, like as we already discussed, like there's basically the ECU and embedded system, the sensors and actuators. But primarily, what we mean by integration of electronics with mechanical system is, for example, now there are accelerator pedal on the vehicle. So essentially, there is pedal position sensor, which translates that function into an electrical signal. Same way for a brake, there is a brake position sensor, and for steering and for all the mechanical functions on the vehicle, it's converted to an electrical signal, and that's how it's been. I mean, the vehicle function translated happens. So electromechanical integration. So the fusion of mechanical components with the electronic system happens in the ECU, enables smart control, monitoring, and automation. It's a core behind the mechatronics and intelligent vehicles. And mind you, most of the sensors today used are smart sensors. So that's also enabling in enrichment of the technology-driven features. So the key examples in automobiles are the powertrain, where the electronic throttle control, hybrid coordination is happening. Chassis, mainly the ABS, stability control, and adaptive suspension. In terms of body, the power windows, HVAC, seating control, LED-based lighting control, etc. In terms of ADAS, it's a sensor fusion with the steering, braking, and acceleration control. So in short, the benefits of integration of electronics with mechanical system is with the seamless interface of hardware and software, right, transforms the vehicle into an intelligent adaptive system, enhancing the performance, safety, and comfort, enables sorry, enables real-time diagnostics and predictive maintenance, helps in improving the energy efficiency and emission control, uh, especially to promote green world, and lays the foundation for software-defined vehicles and connected vehicles. Now let's look at a case study for Bosch scalable ECU platform. So, as I mentioned, Bosch predominantly in the past used to have a custom-built ECUs for fuel injection system. But as the world is moving towards reusability and a platform-based scalable approach, so Bosch also has a scalable ECU platform, which is modular and scalable in nature, agnostic to the power propulsion, and has supports multiple vehicle architecture. In terms of software usability, it is flexible and faster time to market. And principally, the architecture is configured for plug and play to have all the software-defined vehicle adoption. In terms of the platform highlights, it has the common hardware software based across powertrains, which can support powertrain, ADAS, chassis, body. So this is what was highlighting. Unlike in the past where a ECU was dedicated for one particular functionality, today's ECU or hardware and software are capable of multifunctionality. It's only you need to configure it smartly for the desired function and extract the best out of it. It has scalable processing power using multi-core MCUs and SoCs. It is AUTOSAR compliant, ensuring interoperability, and has OTA and modular software, cybersecurity, and IS 2626 compliance. In short, what Bosch through this scalable issue platform has built is a platform for the future where it's an open source where any OEM can take that and build their platform on that and create the software-defined vehicles on that. So in terms of benefits, it reduces the development cost and complexity. helps in faster integration across OEM platforms, improves reliability and lifecycle management, and supports domain and zonal architecture. So, I mean, primarily through this case study, you can understand like how tier one suppliers like Bosch also are transforming in as per the need of the shift in the automotive domain world. Now let's move to the next topic, that is vehicle networking and communication. So, why networking in-vehicle networking is needed? Basically, it helps in reducing the wiring complexity and enables the diagnostics. So, unlike in the past, where in terms of ICE vehicles, each of the sensors, actuators, and the ECU were hardwired. So, if suppose, let's say, a vehicle had 10 sensors, then each of the sensors was hardwired and connected to the ECU. Now, this created unnecessarily lot of wiring complexity, made the vehicle more heavier and made complex, and also as the we need to increase the features and flexibility, it became extremely inflexible in nature. Today, we have more of a communication driven, in-vehicle communication driven protocols, which helps in reducing the wiring harness complexity. Just to give a perspective, for example, a passenger vehicle, a EV passenger vehicle today, because it has a high voltage electric wiring harness and a low voltage wiring harness, easily can weigh more than 60 to 70 kgs. Uh, whereas in ICE previously, with minimal functionality, it used to weigh around 20 to 30 kgs. So that's the extent of complexity in the wiring harness. Also, the advantage when you go for a bus wiring harness protocol is that there is reusability of lot of sensors. Just to give example, suppose let's say in a fuel injected system, engine speed is one of the primary input for computation of lot of activities like fuel injection, engine speed, the actuators, the ignition control, and lot of ABS and lot of stuff. So in the past, these sensors used to be hardwired to the multiple systems which they are connected. Today, the engine controls, the engine speed sensor could be connected to as one subsystem, and through the CAN, those signal can be shared with all the stakeholders in the vehicle. So that's the beauty of having a bus protocol architecture for handling the wiring harness complexity. So networking allows multiple devices to share a common communication bus like CAN, LIN, Ethernet, drastically reducing the number of wires. So it also enables diagnostics and monitoring. Networking allows centralized monitoring of system health and performance. So it also faults, errors, and operational data can be transmitted over the network for real-time data diagnostics. Sorry, this enables proactive maintenance, error logging, and even remote troubleshooting. So a CAN bus in a car can report a failing sensor to the ECU, which can trigger a warning to the dashboard, which in the past only that particular subsystem where it was physically connected would identify. So the benefits are it helps modular system design. So it helps in addition and removal of devices. It enables faster software updates and facilitates complex control strategies by sharing data between multiple controllers, which I just highlighted. So let's look at how an automotive communication protocol overview looks like. Essentially, this image captures the key elements involved in the automotive communication protocol. So the very basic and primitive bus architecture is the LIN, which controls the lighting, seat, mirror, and control low speed application functions. Next is CAN, the controller area network protocol, which is having controlling the engine management, brakes, airbags, etc. Next is the FlexRay, which is used for safety critical system. Uh, and the modern software-defined vehicles predominantly uses Ethernet as on today for high-speed real-time applications like ADAS, infotainment, and a lot of other activity. And then there is the diagnostic and wireless, which enables a lot of predictive maintenance and trouble-free vehicle run. So the purpose of automotive communication is enable data exchange between ECUs, sensors, and actuators in vehicles, ensuring real-time control, safety, and diagnostics. So, as I mentioned, control area network is the backbone of powertrain and body systems. It has a base speed of around 1 megabits per second, and CAN FD can go up to 5 to 10 Mbps. Typical use cases are engine control, transmission, ABS, airbags. So predominantly in the ICE world and all the conventional functionalities are controlled by use case by a CAN. It in terms of the bus, it's having robust fault tolerant message-based protocol. It's a broadcast-based system. On the right shows the image of how a CAN bus is shared by the different nodes on the bus architecture. So LIN, as I said, is a low speed single wire network up to 20 kbps speed, typically used for mirrors, windows, heat controls, and wipers. And in terms of feature, it is a master slave architecture complementing the CAN. FlexRay is more high speed deterministic communication, has speed of up to 10 megabits. And use cases are like safety critical system like drive-by-wire and those sort of stuff. In terms of features, they are dual channel, redundancy, and time triggered. And as I mentioned, today's modern bus protocol is mostly using the Ethernet, automotive Ethernet, which has a very high bandwidth backbone, typical speeds of 100 Mbps to 1 Gbps, used in real-time data streaming like ADAS, camera, and radar fusion, infotainment, and zonal architecture. Features IP-based and supports high data throughput. And in terms of diagnostic and connectivity protocols, UDS or CAN is the predominant protocol used in the industry for fault diagnostics and ECU programming. Diagnostic over IP also is available, and Bluetooth, Wi-Fi, and V2X are used for wireless communication and connectivity. So in terms of the vehicle architecture trends, mostly it is zone oriented. It's having a centralized very architecture with high performance computers and with reduced wiring. So the trends are transition from domain-based to zonal architectures using Ethernet as the backbone, and protocols coexist managed by gateway and centralized vehicle computers. So when I say coexist, mainly it's not that only Ethernet is present in the modern day architecture. I mean, context-based LIN can and FlexRay can exist with the main backbone of Ethernet. In terms of the cybersecurity challenges, primarily four important things to be noted. One is the data privacy, how you protect sensitive information, because as I said, today's vehicle is constantly interacting with the external world. So in terms of the data privacy, it's extremely important. Second is to ensure network hacking is not viable through secured algorithms. As I said, the firmware feature enrichments are always are constantly done through OTA feature. So secure updates uh, through software integrity verification and to prevention of in-vehicle tampering, so that illegal access to the control algorithm and tweaking the functionality could lead to functional loss and safety compromise. So cybersecurity challenges in connected vehicles are attacking the surface complexity, threats to safety critical systems, data privacy and theft, software vulnerabilities, security issues, supply chain vulnerabilities, like because the threat to the data can be in the entire supply chain and cloud and backend risks. So it's a very evolving world where hackers and the developers are constantly updating the security mechanism so that as a customer we are all secure and safe in usage of all the features of the vehicle. So the case study in point is Motherson Ethernet integration. So basically, Motherson were leveraging their vast experience in the wiring harness domain in developing this automotive Ethernet as a backbone network for in-vehicle. So the objective was for high-speed data transmission for infotainment, ADAS, and sensor function. Support scalable architecture for future vehicle upgrades and SDVs. Reduce the wiring complexity compared to the conventional vehicles, and ensure robust cybersecurity and fault-tolerant communication. Sorry. So the key takeaways of this case study is on the left, you see the architecture of how it has been implemented. So there's a centralized ECU with Ethernet as the backbone. Then there are the zonal ECUs communicating with the different ECUs in the zone for different functionality. That's how typically the E architecture in this Motherson Ethernet integration is. So they have successfully integrated and reduced the wiring complexity and has collaborated with OEMs and tier one partners in successfully deploying adoption of this. So the point in case is like Motherson, who have been traditionally a wiring harness supplier. It's being done for multiple applications. So next is the wiring harness basics. So wiring harness is the car nervous system. This image captures how a vehicle and human body, just giving an analogy of between the two. So in terms of wiring harness basics, basically the brain acts like a ECU and a central controller processes the data. Nerves acts as the wiring harness and connects every organ to the brain. Reflexes are the fuse and relays, protect system from injury. And sensory neurons are detects the environment, temperature, speed, and position. Muscles are used for actuators and muscles corollary is actuators and motors, which is for executing actions like moving or steering, braking, etc. So coming to the wiring harness basics, basically the primary importance in wiring harness is the current load balancing. to ensure that electrical circuit operates safely without overheating. So, no voltage drops, distribution of electric current evenly across conductors to prevent overloading and heating. So when overloading happens, then overheating, degrading of insulation, fires, and damage to connected devices happen. So the different techniques used are parallel wiring, where a high current path is split into multiple wires to share the load, proper selection of wire sizing to ensure proper current carrying, fusing and relays for protecting excessive current, and segmenting so that dividing complex systems into smaller sub-circuits for easier load management. Next is the modular harness, where modular harness are designed to simplify assembly, maintain, and scalable. So they are divided into independent modules that can be connected or replaced. Ease of assembly, pre-assembled modules speed up the production. In terms of maintainability, faulty modules can be replaced, especially in field, without disturbing the entire harness. And it is scalable to add new features or systems, for example, infotainment, sensor, without redesigning the entire harness. So it's more modular in approach. The latest trend in wiring harness is the lightweighting materials. So basically, as you know, in electric vehicle, lighter the vehicle, the better it is in terms of energy consumption. So in terms of wiring harness, reducing the weight is essential. So use of lighter wires, insulation, and connectors without compromising on electrical performance safety. So aluminum wires are being explored. Of course, it has compared to copper, it has a lower conductivity and higher thermal expansion. Higher performance plastics for insulation and sheathing, lighter than traditional PVC. Foam or braid shielding reduces weight of shielding while maintaining EMI protection. So, in short, all measures are being taken to ensure that wherever it is possible to lightweight the wiring harness. So, the benefits of that is it improves fuel efficiency both in the ICE and EV, reduces energy consumption, reduces strain on mounting and support structures, and simplifies handling during assembly. So the key takeaways are modern wiring harness is a balance of safety, efficiency, and maintainability. Load balancing prevents overheating, modular harness, simplify production and repair, and lightweighting improves overall system efficiency. Next, we come to the last topic, that is integration and testing. So testing and validation plays an important role in automotive and embedded system, especially now in the context of software driven, where any untested thing can lead to a lot of catastrophic effect in terms of reputation, safety, and a lot of other things. So the goal is to detect early, reduce development cost, and ensure safety and reliability. So the key levels where testing happens is unit testing for the individual functions and modules, integration testing for modules working together, system testing for complete system behavior, and validation and verification where meets the requirements and regulations. So important thing to note is in case of software-driven vehicles, most of the validation happens in the digital world, and yeah, most of they are model-based, so and it is reusable. So this is the typical V where how the vehicle integration and testing happens. So now let's look at software in loop and hardware in loop. So the left is the software in loop, basically where the ECU software functionalities are tested very early in the development cycle on a plant model, and so that majority of the algorithms are in place before we get the actual hardware and the vehicle. The hardware in loop testing happens at a later stage in the development where on actual ECU hardware it is tested and it is tested on real time. and with actual sensors and actuators, and finally it is deployed on the vehicle. So in terms of the key differences between software in loop and hardware in loop, in terms of environment, as I already mentioned, in software in loop is more virtual in nature, but of course mimicking the real world in a model-based environment. In terms of hardware, it is actual issue and but the vehicle run condition is a simulated environment in early stage. Cost-wise, software in loop is more cheaper to do, whereas the hardware in loop requires more expense. In terms of timing, accuracy, software in loop validates the algorithms, but hardware in loop is more real-time and precise. Safety-wise, both are safe, but HL is more real-time. Purpose, as I mentioned, SIL helps in early software validation, because if you wait for the vehicle and the components to be available, then in terms of development, it will be delayed. And so typically, software in loop is used in early development, and hardware is used when the actual hardwares are available. And in terms of the typical development workflow, it's like model and algorithm is first developed, then you have the software in loop, and then hardware in loop, followed by vehicle testing and production validation. So in terms of functional safety consideration, this is a very extremely important thing in the current automotive domain. It ensures safe operation of vehicle electrical system even during faults. And the main goal is to avoid unreasonable risk due to malfunctioning behavior. So the key concepts involved is hazard analysis and risk assessment, and based on that you do the ASIL A to D classification, where D is the severest. Then define the safety goals, and then have functional and technical safety concepts. In short, it covers the entire life cycle of the vehicle, right from concept, development, production, operation, and decommissioning. So in short, functional safety ISO 26262 involves risk management, hazard, ASIL rating, and safe operation of the vehicle, especially related to electrical functionality. Now, take a case study of ultra wiring harness design, Bosch best practices in validation. So, Bosch, I mean, supplier of advanced wiring harness. So, increase in complexity is due to EV, ADAS, and connected vehicle integration. So, most important thing is deployment of simulation-based validation. So, digital mockups for routing and packaging, especially deployment of thermal flow simulation for optimization, and fault tree and FMEA analysis before prototype build. All this helps in the success ratio and gaining the confidence of deployment of the harness in real world. So the tools used are CATIA harness, capital harness systems from Mentor Graphics, harness validation bench, load simulation and fault detection. And important thing is data correlation between simulation and physical test, so that you keep on improvising on the models. So the lessons learned from this Bosch approach is early stage simulation reduces prototype iterations. A design validation plan aligned with DFMA ensures test relevances and reduces iterations. Standardized connectors improve serviceability, and data-driven validation improves reliability prediction, especially in complex harnesses with multiple functionalities like this. Now let's move like what are the key skills required for a modern mechanical engineer in especially in the software defined era. Importantly, the core mechanical know-how, especially in thermal and structural in terms of mechatronics and electronic integration, in terms of software simulation, especially the bus protocols and how it interacts, in terms of functional safety and cyber security, also in terms of model-based system engineering and continuous learning and adaptability, and important to collaborative and agile practices, because unlike in the past, today the entire activity is collaborative in nature between the OEM, Tier 1 and the entire ecosystem. So, so the new skills required for a mechanical engineer is in terms of good knowledge in mechatronics, software defined in terms of sensors, actuators, the vehicle in communication networks, and also cross-functional engineers who can collaborate across domain of collaborative work in nature. So, and the core area of focus would be EV, ADAS, SDV, and connected vehicles. This is where the automotive domain of the future is predominantly pointing to. So, with that, I come to end of my presentation, and I'm now more than willing to take the questions. Thank you.
Thank you, Mr. Ravindra. There are a couple of questions in the chat window. I'll read it out for you. Mr. Ravindra, am I audible?
Yeah, you're audible. Please go ahead.
Yeah. So Mithun has a general question. So when can we see SDVs on road? Which are the OEMs that are ahead in terms of like bringing this to a reality?
So, I mean, in terms, see, as software-defined vehicle is a concept. So today's EVs are nothing but a software-defined vehicle. So the Mahindra, Tatas, all their electric vehicles are nothing but software-defined vehicles, which are already on the road. And also, for example, the two-wheelers of, let's say, Ather, Ola, Bajaj, all are, of course, they're, I mean, in terms of software defined features or functionalities, they are slightly less complex compared to Mahindras and Tatas. But most of the electric vehicles are already software driven vehicles.
Noted, sir. Varghese asks, the shift towards SDV means more complexity in repair of vehicles and related costs. How are these aspects considered in the case study?
Yeah, so actually it is the corollary. So when we are moving from a mechanical driven ICE to a EV SDV world, so in terms of wear and tear, the number of parts are less. Second, because it's a connected vehicle, in terms of remote diagnostics and monitoring and predictive maintenance, the vehicle health is being closely monitored. And because of deployment of artificial intelligence and machine learning, so there is a lot of technology being deployed to ensure that any abnormality in the vehicle health monitoring is picked up very early, and so the downtime of the vehicle is much lesser. And in terms of diagnostics, most of the activities happen remotely.
Noted, sir. Kavita wants to know on the Motherson case study, which OEM has done that?
So, I mean, basically, Motherson was a POC, which they were showcasing to a lot of OEMs.
Okay, sir, got it. Guys, any other questions? We have another 5 minutes left. If you have any other questions, please share it in the chat window. Ravindra will be happy to take it up. Meanwhile, I'm dropping the feedback form on the chat. Please take a couple of minutes to fill it up. Sir, Nitesh wants to know, when SDVs increase on roads, the threat of EMC or electrical interference between vehicle becomes more complex and may fail, right?
So, I mean, today also there is a very stringent EMI/EMC norms. for be it ICE or SDV vehicles. You are right. In terms of the design, it is going to be much more complex. But in meeting the EMI EMC norms, it is the same, whether it was ICE vehicle or SDV. But in terms of design, it's much more complex. But we also have to keep in mind today's semiconductors are much more robust, having much more thinner wafer technologies and have a much higher inherent EMI EMC capabilities compared to the earlier generations. So overall, it's like a multiple shift happening both in design and the semiconductor technology available. And of course, the simulation and design with a lot of simulation tools available. As I showed in the last case study, for example, a wiring harness. Traditionally, it was being done in more through a mechanical means, but today using the softwares, a lot of things are predicted and simulations, virtual simulations are done, digital virtual simulations are done. Same is the case for EMI/EMC also.
Thank you, sir. Piyush wants to know what are the key architectural changes between ICE, EV, and SDV in terms of ECUs, communication, and computing?
So, in terms of the computing, as I said, in the SDV, mostly it is a zonal architecture where when I say zonal architecture, there is a high power computer in different zones of the vehicle, left, right, front, central. And then it is the multiple functionalities of the ECUs are connected to the zonal ECUs. And through the Ethernet backbone, they talk to each other. Whereas in case of ICE, it's like more of a distributed ECU. So, for example, fuel injected ECU, there is one ECU with all the sensors, actuators in one coming to that ECU. ABS, there is one ECU. Body control, there is one ECU. So, there is a vast change compared to the ICE architecture. Here it is much more in terms of ECU, they are pretty much standard, but the way it has been configured and the way it is software enabled, context sensitive, makes how the SDV architecture works. And of course, in terms of computing power, in terms of memory, and in terms of the processing, today's SDV embedded systems are much more powerful compared to the ICE world, simply because it has to handle live streaming data and other things real time.
Thank you, sir. Folks, we will close in the next couple of minutes. If you have any other questions, please share it in the chat. I've also shared the feedback form in the chat window. Please fill it up. We'll share the recorded session with everyone who have attended the session. Any other questions for Mr. Ravindra? Sir, Vaibhav is asking what are the challenges for EMI EMC in EVs?
Yeah, it's a good question. So definitely with more power, more performance, more feature, definitely there is a trade-off in terms of meeting EMI/EMC requirement, especially like for example, in case of EV with the traction motor and with a lot of motors having. So with high switching frequency for the traction motor, the DC-DC converter and other things. So there is a lot of EMI/EMC related noise being generated. So it's very important how you handle the switching, how the layout of the power circuits are incorporated, and ensure that there is no crisscross between the low switching and high switching, and also in the vehicle. I would also say important thing is apart from the electronics in the vehicle harness layout. Also, it is very important to ensure that the LV, HV, and all those things are taken into proper consideration, because there's a lot of length of wire moving around. So if the care is not taken in terms of from the EMI/EMC perspective, then however good your controller or other design is, if the wiring harness is not done properly, then that itself acts as an antenna and negates the good work in the electronic control and other units. So it's a holistic approach you need to take.
Thank you, sir. There are no more questions, sir. We can go ahead and close the session. Thank you once again for taking your time out today, sir.
Thank you very much, participants, for today's session, and hope it was enriching and will be helpful in your daily work life. Thank you very much.
Thank you, sir. Thank you to all the audience for joining on a Friday evening. Thank you, guys. Kindly take a couple of minutes to fill up the feedback form. We'll share the recording of the session.